Okay, so the second speaker for today is Zhou, a Western Canada High School alumni that has found both interest and success in the fields of biology and chemistry throughout his years in high school and university. During his time at Western Canada High School, he placed first in both the Canadian Biology Olympiad and the Canadian Chemistry Olympiad. Currently, he studies biochemistry and computer science at Yale University. Today, he will be introducing the uses of modeling in his work and studies and different modeling related lab techniques he's used, as well as how high school students can become involved in modeling. Jeffrey, if you could please start sharing your screen now.
Yeah. Okay. So thank you, Jasmine, for the introduction. Today I'll be talking a bit about biological systems, and I'll kind of give an example of something I've worked on in the past, and hopefully like you'll be able to understand like the thought processes that go through it by the end of this talk. So yeah, Jasmine already did a bit of an introduction about me, but yeah, I graduated from Western Canada High School in 2017. I have a background in biology and chemistry. And one thing that I didn't mention is that I also have, in high school I had a like pretty extensive background in math, but before I entered Yale, I actually had no experience programming. So it was only in my first semester at Yale that I first started taking a computer science class, and I found it really interesting, which is what led me to double major in computer science as well. And from there, I began to integrate computer science into like my studies and work, and I use it a lot in my research as well. Aside from that, like I have some hobbies such as like video games, baking, and origami. So if you're interested in any of those, like feel free to let me know and we can chat about it. Yeah, moving on. So I'm not sure how many of you here have taken high school chemistry. So if you have any questions about this actual like content, feel free to ask that in the Q&A and I can answer them in real time if it pertains to what I'm talking about right now. But basically our problem is, like a big problem in biology is that you have all these biological molecules and you want to model how they interact. So, well, like one of the simplest examples is you have two molecules and they combine to form a complex, right? So here our example is we have these receptors, which are these yellow things on the bottom, and we have these ligands on the top, which are these floating blue things. And when they combine, they can do things such as like cell signaling or any like host of different things that happen when they react. And as you can see from this animation, like it's not really just like something that's like super well defined, right? These ligands float around and they bind to the receptors, and then they also unbind as well. And yeah, it's basically like the chemistry. It's basically the concept of equilibrium if you've heard that in your chemistry classes. And so from there, what we can do is model it as this chemical reaction. So receptor plus ligand becomes a complex, and then we have these equilibrium arrows to imply that it can go in the opposite direction as well. And another like basic like chemical concept is that we have these rate constants Kf and Kr to represent going like forwards and backwards from this reaction. And then yeah, so like with this simple reaction, we can actually get started with like modeling our system. So we'll have a differential equation, which is basically just a complex way of saying we're gonna model how the system like changes over time. So then the C in square brackets represents the concentration of complex that we have. So that's what we're most interested in seeing. So how the concentration of the complex changes over time is going to be equal to this first term of this reaction is going to be how we're modeling the forward direction of the reaction. So that's going to depend on the concentration of the ligand, because if you have more ligand, it's going to make the reaction go faster. It's also going to depend on the concentration of the receptor, because if you have more receptor, the reaction is also going to go faster. And lastly, it's going to depend on this rate constant. Yeah, so I think in like high school chemistry, this is covered. So hopefully that's like not too like out of here. But yeah, that's how we got this first term. It's the rate constant for the forward reaction multiplied by each of the two reactants that are involved in that reaction. At the same time, though, we also have this competing reaction in the same system, right? So you can see that like sometimes the complex dissociates and then we get like a ligand and our receptor back. And so that's modeled by the second term in this equation, which is KRC. So that's going to be the reverse rate constant, KR, multiplied by the concentration of the complex, right? So far so good. That's just like a basic differential equation that we have for our system. And okay, so there's two types of ways you can solve like these mathematical problems a lot of the time, and then one is called an analytical solution, which is where you find an exact solution, and the other is called a numerical solution. So an analytical solution is basically a way of getting the exact answer, while a numerical approach like gets you closer and closer to the right answer until you basically just approximate the right, but it doesn't actually tell you exactly what it is a lot of the time. And the analytical approach for this equation like takes a bit of work, and I'm not going to go into details, but if you're interested in finding how much of the fraction of the receptors are bound in the complex, it comes out to this. Basically, you like integrate the differential equation and solve for Z, and then you get an equation that looks something like this. And just some terminology, like R naught is the starting amount of reactant, so R naught is the starting amount of receptor, so it's basically equal to the total amount of receptor you have, and same with L naught. L naught is the total amount of ligand you have, as well as like how much ligand do you have total, because basically you're starting with like all of your ligand and all of your receptor, and you're trying to model what happens as you mix them over time. Okay, so imagine if we didn't have this analytical approach and we wanted to just like approximate this using a mathematical model. So that's what we're going to look at on the next slide. So we can, what we can do here is use a numerical solution to kind of get closer and closer to the answer until it's basically correct for like any purposes that we want. And so numerical solutions use numerical approximations rather than looking for exact solutions. And just to give an example for this, so you have some of the intuition of what we're doing with this differential equation. So you want to find the root of this function, right? But like it's not some like simple algebraic form, so you can't actually just solve to find the zero exactly. But what you do know is that at x equals a1, f of a1 is above 0, and at x equals b1, f of b1 is below 0. So what you can do then is compute the average of a1 and b1, so that's going to be here, b2, and then see if that value is above or below 0, right? And like here, it's going to be below 0, and what that means is that since f of b2 is below 0, you know that you basically like shorten this interval in half, and you know that your 0 is going to have to be between a1 and b2. And you can do the same thing again. You can take the average of a1 and b2, which is going to be a2 here, and now that a2 is above 0, you know that your 0 has to be in this interval between a2, f of a2, which is positive, and f of b2, which is negative. Then you repeat again. You take the average of these 2 points. You find that f of a3 is above 0 again. And you just keep going until you get like an infinitely close approximation to what the 0 actually is. And in this case, we can do something similar with what's called Euler's method, which is a way of solving ordinary differential equations, which is the idea between Euler's equation is that even though you can't find this rate of change directly, what you can do is, so you know how much ligand you have at the beginning, and you know how much receptor you have at the beginning, and you know how much complex you have at the beginning. So you can calculate how fast the complex changes as a function of time instantaneously. So you can find like the very start of the slope, and then you pretend that that slope just doesn't change over a very short interval. And after that short interval, you recompute the slope based on what you then know about like the ligand, receptor, and complex at that point of time. And yeah, you just keep going there until you approximate it over the time interval that you're interested in. Okay, so now I'm going to show you some code that actually puts this into practice. Okay, so yeah, basically what I did here was this first section is all about using Euler integration, which is that numerical method I just talked about. Whereas for here, I just plotted the equation solution from the slide before. Let's just take a look at how they compare in practice. Okay, so I graphed both, and as you can see, like this is what it came out to. So red is the numerical solution, which is using Euler's method, whereas green is the exact analytical solution. And what you can see is that like they're not off too much. And like since we have like a graphical here, I will like go over Euler's integration method again to see like exactly what it's doing. So starting from time 0, we know how much ligand, receptor, and complex we have. And then based on that equation we had, we can compute how fast it's going to change over time. And we just assume that it has that same slope all the way until this next data point. And then when we reach this point, we recompute the slope. And yeah, we do this by using the new receptor, ligand, and complex concentrations we have from this point. And then, so after we recalculate the slope, we see it's leveling off a bit, and we continue until the next data point. And yeah, we just keep going like that until we finish our entire approximation. And yeah, let's play around with this a bit and see what happens if we change the time step. So the time step is basically how far it travels before our numerical method recomputes the slope. So this was with a time step of 0.05, but let's see what happens if we change to 0.01. Okay, yeah, so you can see that like by decreasing the time step, it looks even closer to the numerical solution now, or sorry, to the analytical solution now. And that's because basically we're adjusting for any like incorrections in the slope like much more quickly now. So like after a short time interval, we're gonna adjust the slope. And yeah, it basically comes out to a line that's almost exactly the same as the analytical solution. And we can go even further and reduce the time step even more. I'll take out the circles so that it's easy to see. But yeah, like these two lines are pretty much exactly on top of each other. And like remember that this red line is actually just an approximation. So we did like if you did I'm gonna go back to my PowerPoint one sec. If you didn't know that like this was a solution at all you had to do is model this differential equation using Euler's method, and you get results that are pretty much exactly the same. And even though like that was helpful in this case where like we did have a analytical solution already, a lot of the times when you're modeling like different things, you can only have a numerical solution. And so it can like model these like super complex systems and approximate it to a point where like it's basically good enough for like anything you might need. And like one example I can think of off the top of my head is in physics, where if you have like 3 planetary bodies, or like three big bodies in mass, it's like it's pretty much impossible to define any analytical solutions that model the behavior of 3 bodies exactly. And you're gonna have to use like numerical methods for that, like kind of like what we did here. And they'll get you like pretty much close enough to the solution for like any purposes that you might need. Yeah, so that was basically the example I wanted to talk about, and I think it illustrates pretty well why mathematical modeling can be so powerful, because like it's not all the time that you can come out with a nice clean solution like this that gets you exactly what you want. And so a lot of the time you might just have to settle for an approximation, which mathematical modeling does well. And then lastly, I just have some like tips for high school students who are interested in getting into modeling here. And so, yeah, it's pretty early because like, as I mentioned before, I had no computational experience, but it's really good that so many people are interested in getting into modeling so early. And so my first tip is basically just to think about how questions in your day-to-day lives can be answered quantitatively. Yeah, the first step to like doing biological modeling is finding a problem that you're interested in. So just look around and keep an eye out for phenomenon that you want to understand better, and then think about like why or like how you might model that. And if it's too complex at first, you can like always go to a smaller scale, and then like keep going, like zooming in smaller and smaller until you get to somewhere where you feel like you can comfortably model it, and you can build up from there. And the second thing is to hone your writing and communication skills, because a lot of the times, like a lot of the work that goes into this modeling and like computation techniques is going to be like really theoretical, and it's going to be like very unapproachable for people with like a mathematical background. So one thing to work on is communicating your ideas and your results to people who might not have as like extensive a background in the field as you. And like the last one is more like an opportunity, but yeah, one of my good friends at Yale entered a lot of mathematical modeling competitions in high school. And so some of the ones that he took were like the Consortium for Mathematics and its Applications High School Mathematical Contest and Modeling, as well as MathWorks as well as the MathWorks Math Modeling Challenge. And so these are opportunities for you to enter and compete for prizes around, like, these are both international competitions, I think, where you can just sign up with a team and model whatever you would. I think they actually, no, I think they have a question that you have to work on each year, but this is also a good opportunity for you to get involved in modeling and just like practice a bit. And compared to like traditional like pure math competitions, these might be like a bit less intensive because you're working on your models over a longer period of time, and you get for like both of these, I think you get to work with a group, so that's kind of pretty fun as well because you get to work with your friends basically. Yeah, so that's pretty much it for my presentation, and I hope it was helpful for learning a bit about like how you can model biochemical situations.